Here we'll talk about the mechanism for the Wittig reaction. I've copied down the general scheme from a previous video. You don't necessarily need to rewrite this. I'm just going to reference it as we work through the mechanism. We have an aldehyde or ketone starting material. We add an ylide. In the previous video, we talked about how to form ylides and the resonance stabilization of the ylide. And then this forms an olefin molecule with a new carbon-to-carbon bond and very stable triphenyl phosphine oxide. Okay, so assuming we formed our ylide and we are adding a ketone to that solution with the ylide, we will use cyclohexanone in the mechanism as an example. So this is our ketone. Remember, when we have a ketone, we have an electrophilic site that is this carbon here. And then in the ylide, it's more clear to see this when we draw the carb anion form of the ylide, so carbon with a negative charge. We'll say it's bonded to 2 hydrogens and a positive phosphorus with 3 phenyl rings. We have an electrophilic carbon in the ketone or aldehyde, and in the ylide, we have a nucleophilic carbon. Just like when we form an enolate, we have a nucleophilic carbon in the enolate. I'm going to use a couple different colors in the mechanism here. So our nucleophilic carbon has electrons it is willing to share with the electrophilic carbon. So we create a new carbon-to-carbon bond there. Now we know the pi bond between carbon and oxygen will break. Instead of that pi bond going up to the oxygen, those electrons in the pi bond are more attracted to the phosphorus in the ylide, which is positively charged. So this forms now a 4-membered ring. This is referred to as a 2+2 cycloaddition. All right, we are doing an addition reaction. 2 atoms from the ylide and 2 atoms from the ketone or aldehyde are involved in this cycloaddition. So the result of this step, I'm going to draw the 6-membered ring that is still a ring. Now, the carbon to oxygen bond is a single bond. We have a new carbon-to-carbon bond that was formed with the blue arrow, so from the nucleophilic carbon to the electrophilic carbon. So we have a CH2 here. We have a new oxygen to phosphorus bond, so that was formed with the green arrow. And phosphorus is still bonded to the 3 phenyl rings. And then the carbon to phosphorus bond has not broken. So we still have that carbon to phosphorus bond. Now notice we have all neutral atoms here. Oxygen has 2 bonds, carbon has a total of 4, phosphorus has a total of 5, and that's a neutral bonding pattern for phosphorus. So we formed our 4-membered ring intermediate. This is characteristic of Wittig reactions. You do the 2+2 cycloaddition and have a 4-membered ring. Now to form the final product, remember the final product has a carbon-to-carbon double bond and forms triphenyl phosphine oxide. Well, we have another 2 arrows In the carbon to phosphorus bond, the carbon holds onto those electrons a little bit more. So the carbon will take the electrons from the carbon to phosphorus bond and then form a pi bond, while at the same time the carbon to oxygen bond forms a pi bond between oxygen and phosphorus. So we've broken 2 single bonds and formed 2 pi bonds in this step. So we have our 6-membered ring. At the carbon on the right, we now have a pi bond to the CH2 group. And this is our alkene or the olefin. And then to the triphenylphosphine, we have a phosphorus to oxygen double bond. That's our triphenylphosphine oxide product. So here is the alkene, or in other words, the olefin. Here's the triphenylphosphine oxide. Now this alkene that's formed through the Wittig reaction, having a less substituted carbon, or that's part of the double bond. We've talked about Zeitz's rule before. More substituted double bonds are more stable thermodynamically. So this is a less thermodynamically stable product. So this is difficult to prepare with other methods. It's easier to prepare with a Wittig reaction. So let's write this note here. Difficult So this alkene is difficult to prepare with other methods. So we prepare it with the Wittig reaction, but difficult to prepare with other methods because the isomer that I'm referring to is another 6-membered ring with a methyl group, and the pi bond is within the ring. This is a more thermodynamically stable isomer than the alkene that's formed through the Wittig reaction. So using other methods in Organic 1, we talked about elimination reactions that form a carbon-to-carbon double bond. And the more thermodynamically stable alkene would be favored in those reactions. But with the Wittig reaction, we can form this less thermodynamically stable molecule, and that's why it is favorable. So it is a 2-step mechanism. Once you've formed your ylide and you add your ketone or aldehyde, it's a 2-step mechanism. First you form a ring, and then in the second step you break 2 single bonds in the ring and you're forming 2 pi bonds to form the olefin and the triphenylphosphine oxide.